तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. Today we are starting the second module on losses in prestress. In the first lecture in this module, we shall first get familiar with the notations in the geometric properties and load variables. Next, we shall go to the first type of loss in prestress concrete structures, that is the elastic shortening, and we shall understand the phenomenon of elastic shortening for pre-tensioned and post-tension members. In either type of the prestressed structures, we shall look into examples of axial members and bending members. The commonly used geometric properties in this prestressed member are explained in this slide. AC is the area of the concrete section. That means, given the total section of the member, if we subtract the area of the prestressing steel, then the remaining area of the concrete is termed as AC. There can be, of course, difference between AC and the total area A if the duct size is large. The second notation is AP, which is the area of prestressing steel, that is the total cross-sectional area of the tendons. The third is the area of the prestressed member, which is the summation of AC and AP. There is another definition which is used in elastic analysis, that is the transformed area of the prestressed member. This is the area of the member when the steel is substituted by an equivalent area of concrete. The transformed area is given as AC plus the modular ratio times the area of the prestressing steel. If we substitute back the expression of the total area, then the transformed area is given as the total area plus the modular ratio minus 1 times AP. The modular ratio is defined as the ratio of the elastic modulus of the prestressing steel divided by the elastic modulus of the concrete. Now, the modulus of concrete can change with time. In our elastic analysis, we may stick to the short-term elastic modulus, and then the modular ratio is defined just based on the short-term elastic modulus. If we use the long-term elastic modulus of concrete, that means we are including the effect of creep in the definition of the modular ratio of the member. To explain it by figures, on the left is a cross section of a rectangular prestressed member. If we look into only the net area of the concrete cross section, that is represented by AC, and the total area of the prestressing steel, here we have denoted within one circle, that is represented as AP, and this prestress section is equivalent to a transformed section where the full section is considered to be of concrete. That means the prestressing steel has been substituted by an equivalent area of concrete. Now, this transformed area is considered to be made up of only one material, and that is used in the analysis, elastic analysis, which is similar to an elastic analysis of a homogeneous material section. Next, we are learning the definitions of the centroids. The first one is the CGC, the centroid of concrete, or you can say the center of gravity of concrete. The centroid of the gross section is defined as CGC. Here we are not deducting the area of the prestressing steel just for simplicity in the computation. We should note that the CGC may lie outside the concrete section. An example is given for a box girder. The centroid of the section is lying outside the concrete, but it is lying inside the hollow space of the box girder. The second definition is the centroid of the prestressing steel, or the center of gravity of the prestressing steel, and we shall denote that as CGS. The CGS may also lie outside the tendons or the concrete of the section. In most of our calculations, we do not consider the individual tendons in the prestressed member, but we do the calculations based on the total area AP and the location being considered at the CGS. Now, there are two types of section are being shown. On the left is a box girder where both the CGC and CGS are lying inside the hollow space of the box girder, and on the right hand side we are seeing an eye girder where the cross is the CGC and the blue circle is the CGS. That is, when we do our computations, these are the two most important locations that we are concerned of. The other important geometric properties are, the first is the moment of inertia of the prestressed member. This is represented as I, and this is the second moment of area of the gross section about the CGC. Remember that for an elastic section, the neutral axis lies at the CGC. And the second one is a more refined calculation of the moment of inertia, that is the moment of inertia of the transformed section, where the second moment of area is calculated about the centroid of the transformed area. Now, the first one, I, is a simplified form of the second one, which is IT. Another most important variable that we shall use in our calculations is the eccentricity, which is the distance between the CGS and the CGC, the vertical distance. Now, if the CGS lies below the CGC, then we shall consider the eccentricity to be positive, and if the CGS lies above the CGC, then the eccentricity will be considered to be negative. Now, for the box girder, here we see that the E is the distance between the CGC and the CGS, and here it is positive. And similarly for the eye girder, here also the E is positive because the CGS is lying below the CGC. Among the load variables, Pi will represent the initial prestressing force which is applied by the jack. This is the force which is recorded by the gauge in the jack. The second one is P0, which is the prestressing force after immediate losses. That means the actual prestressing force that is transferred to the concrete section is lower than the value which is recorded by the gauge in the jack. It is lower because of the immediate losses of elastic shortening, friction and sitting of the anchorage, and that we shall denote as P0. The third one is PE, which is the effective prestressing force after the time dependent losses. As we learned earlier that the prestressing force drops with time, and after several years it gets stabilized to a final value, and that value will be referred to as the effective prestressing force, and it will be denoted as PE. Next, we are moving on to the losses in prestress. Unlike reinforced concrete member, the strength of a prestressed concrete member is not constant throughout its lifetime. Even if we neglect the deterioration, the prestressing force drops with time due to the time dependent losses. Hence, the calculation of the losses is very important in prestressed concrete applications. In the prestressed concrete applications, the most important variable is the prestressing force. Now, in the earlier days, it was observed that the prestressing force does not stay constant, but it reduces with time. Even during prestressing of the tendons and the transfer of prestress to the concrete member, there is a drop of the prestressing force from the recorded value in the jack gauge. The various reductions of the prestressing force are termed as the losses in prestress. Now, in this chart, we are trying to understand the various losses under different sections. The losses in prestress can broadly be classified under two groups. One is the immediate losses, which is shown on the left side, and the other is the time dependent losses, which takes several years till the prestressing force gets stabilized. Now, out of immediate losses, the important one is the elastic shortening, which is the shortening of the concrete member when the prestressing force is transferred to it. It's an immediate shortening. And then the second one is the friction. The friction is the drop in the prestressing force along the length of the prestressing tendon because of the curvature in the prestressing tendon. And the third one is the anchorage slip. That means after the jacks have pulled the tendons, when the tendons are cut, they sit in the prestressing member, and during the sitting in the post-tension prestressing member, there is some loss because the wedges gradually fits within the blocks. Now, the loss due to this sitting of the anchorage is called the anchorage slip. Among the time dependent losses, we have already studied the phenomenon under the material properties. Creep and shrinkage are typical behavior of concrete. Creep is the deformation with time under a constant load. Shrinkage is the deformation with time due to loss of moisture, and relaxation is a property of the prestressing steel, which is the drop in the stress under a constant strain with time. Now, in today's lecture, the following section will quantify the loss due to elastic shortening. Now, in pretension members, when the tendons are cut and the prestressing force is transferred to the member, the concrete undergoes immediate shortening due to the prestressing force. The tendons also shorten by the same amount, which leads to the loss of prestress. The elastic shortening is more of a concern in a pretensioned member. Let's try to understand this by the animation which we had seen before, and this animation will clarify the phenomenon of elastic shortening during the transfer of prestress. At first, in the prestressing bed, the tendon is anchored at the bulkheads, Next, we position the jack at one end, and then we apply the tension in the tendon. After the shuttering is placed, the concrete is cast, it is cured and hardened to the desired strength, and then the tendon is cut. Now, when the tendon is cut, note that the concrete will shrink from its original length to a reduced length, and that shortening is called the elastic shortening. Note this process carefully. See, as the prestressing is being transferred, this concrete member is reducing in length, and that reduction is called the elastic shortening. If the tendon is placed eccentrically, then it will also deflect upwards, which is called cambering, along with the elastic shortening. That means in pretension member, the elastic shortening occurs when we are cutting the tendons at the end and the prestressing force is getting transferred to the concrete. The system comes into an equilibrium after the elastic shortening. In post-tension members, the phenomenon of elastic shortening is different from that in pretension member. If there is only one tendon, then there is no loss because the applied prestress is recorded after the elastic shortening of the member. See, in post-tension members, as the jack gets the reaction from the concrete member itself, when the jack is applying tension in the tendon, the member is shortening, and after the shortening stabilizes, we are recording the final force. Hence, we do not consider the elastic shortening as a loss because we are recording the prestressing force after the concrete member has shortened. This is true if we have just one tendon for post-tensioning the member. But if you are having more than one tendons, then when we are applying tension to a subsequent tendon, the tendons which were tensioned earlier, they will be undergoing some elastic shortening. That means for more than one tendon, if the tendons are stretched sequentially, there is loss in a tendon during subsequent stretching of the other tendons. Now, in this figure, we shall try to understand the process of elastic shortening in a post-tensioned member. In a post-tension member, first the concrete is cast on the casting bed. There is a duct which is a hole in the concrete member. Then through the duct we pass the tendon, and then we apply the anchorage at one end. We position the jack at the other end, and when we are applying tension in the jack, notice that this member is undergoing elastic shortening. Now, once this member has come to a stable length, then we record the jacking force, and hence whatever shortening has occurred will not get reflected in the value of the force that is recorded by the jack. Hence, if we are just having only one tendon, then there is no elastic shortening from the value of the force that is recorded by the jack. But if we have more than one tendons, then the tendons which are tensioned earlier, they will have a loss during the tensioning of the subsequent tendons. Now, how do we calculate the loss in prestress due to elastic shortening? The elastic shortening loss is quantified by the drop in the prestressing force in a tendon due to the change in strain in the tendon. Now, that is obvious from a Hooke's law that if we have a change in strain, there will be a change in the stress. That is why First, what we are trying to quantify is the change in the strain. It is assumed that the change in strain in the tendon is equal to the strain in concrete at the level of the tendon due to the prestressing force. Now, this assumption is called strain compatibility between concrete and steel. For a pretension member, there is bond between the prestressing tendon and the concrete. For a post-tension member, there is bond when we are grouting the post-tension members, and hence we can consider strain compatibility between the concrete and the steel. That means whatever the strain the concrete undergoes at the level of the steel, the same strain is reflected in the prestressing tendon, and the prestressing tendon also undergoes the same change in strain as equal to the strain in the concrete. The strain in the concrete at the level of the tendon is calculated from the stress in the concrete at the same level due to the prestressing force. So, that means our next step is how do we calculate the strain in the concrete. So, the calculations are finally based on the prestressing force which we are recording. Hence, the strain is calculated from the stress that is generated in the concrete at the level of the prestressing steel due to the prestressing force. A linear elastic relationship is used to calculate the strain from the stress. Now, the following slide explains the quantification of the loss. That means the drop in prestress is equal to the elastic modulus of the prestressing steel times the change in strain. The change in strain in the prestressing tendon is equal to the strain in the concrete. The strain in the concrete is equal to the stress in the concrete divided by the elastic modulus of the concrete. Now, the ratios of the two elastic moduli of the prestressing steel and the concrete is denoted as the modular ratio M. Hence, the basic equation to calculate the loss in prestress due to elastic shortening is equal to the modular ratio times the stress in the concrete at the level of the tendon. Now, as we know that there need not be a single tendon, there can be several tendons in a concrete member. For simplicity, the loss in all the tendons can be calculated based on the stress in concrete at the level of CGS. Now, that means here comes the utility of the CGS, that we are considering that as if all the tendons are concentrated at that location, and we are calculating the stress in the concrete at the level of the CGS. From there, we are calculating the loss in the prestress. Now, this simplification of course cannot be used when the tendons are stretched sequentially in post-tension members, because in a post-tension member the calculation is more involved. It is a sequential process, hence we cannot club together all the tendons to be located at the CGS. Let us first look into the pre-tensioned axial members. The axial members means that we are neglecting the eccentricity of the CGS, as if the member will just shorten elastically, there will be no effect of cambering. Now, in order to calculate the stress in the concrete at the level of CGS, we are trying to understand the static equilibrium. When the prestressing force is transferred, the concrete member has an original length. Now, during the process of transferring, this axial member comes to an equilibrium with a reduced length after elastic shortening, and the prestressing force also drops from the initial value to a value P0. The stress in the concrete is given as remember this expression is at the static equilibrium, that is given as P0 divided by the area of concrete which we are denoting as AC. That means delta Fp is equal to the modular ratio times P0 by AC. But here there is a difficulty in using this expression. We do not know P0 correctly because the value that we record by the jack is Pi. Now, it is easier if we can transform this equation in terms of Pi. Now, we shall see later that this expression can be again written as the modular ratio times Pi, which is the force we are recording at the jack, divided by the transformed area. Now, this can be simplified to a product of the modular ratio times Pi divided by the gross area. The difference between the gross area and the transformed area may not be significant if the amount of prestressing still is small. Thus, to summarize, the stress in the concrete, which is P0 by AC, can be equated to the stress in the transformed section due to the initial prestress. Now, the following slides will provide this derivation. And also we have seen that the transformed area AT can be approximated to the gross area A for computational simplicity. Now, we are trying to understand the change in strain due to the elastic shortening. When we are stretching the steel, there is an initial strain in the prestressing strand, which is the strain calculated based on the original length of the concrete member and the length of the tendon before the stretching. This strain is denoted as epsilon Pi. Next, after elastic shortening, the concrete undergoes a strain of epsilon C, and the final strain in the prestressing steel is denoted as epsilon P0, which is calculated from this final length of the concrete member and the original length of the prestressing tendon. Now, the strain in concrete due to elastic shortening epsilon C is the difference between the initial strain in the steel, which is epsilon Pi, and the residual strain in the steel, which is epsilon P0. Hence, epsilon C is equal to epsilon Pi minus epsilon P0. This is just a geometric relationship. Now, each of these strains can be equated to the corresponding forces by the elastic equation. Epsilon C is given by the force which is occurring after it has come to static equilibrium, divided by the area of the concrete and the modulus of concrete. Epsilon Pi is given by the initial prestressing force which is applied by the jack, divided by the prestressing steel area and the modulus of the prestressing steel. And epsilon P naught, which is the residual strain in the prestressing steel, is equal to the residual prestressing force P0 divided by the area of the prestressing steel and the modulus of the prestressing steel. Now, substituting these expressions in the expression of the strains, epsilon C is equal to epsilon Pi minus epsilon P0, we get this top equation, and once we transpose those terms as like this, that means what we are doing is we are bringing the terms with P0 on one side and the term with Pi on the other side, and we are also substituting the ratio of EP and EC by the modular ratio. Once we do this transposition and substitution, we come to this expression, which is the stress in the concrete that is calculated based on the stress at transfer P0 by AC, that is equal to the initial prestress that we record by the jack gauges divided by the transformed area. So, this equation is thus helpful because we are not able to calculate P0, but we are able to calculate Pi. Hence, we can substitute Pi by AT in place of P0 by AC. Let's use this expression to solve a problem. A prestressed concrete slipper produced by the pretensioning method has a rectangular cross section of 300 by 250 millimeters. It is prestressed with 9 numbers of straight 7 millimeter diameters at 80% of the ultimate stress of 1570 Newton per millimeter square. We have to estimate the percentage loss of stress due to elastic shortening of concrete. Consider the modular ratio to be 6, and we have already seen that the Pi is equal to 0.8 times Fy. Now, here the prestressing tendons are divided into 2 groups. 4 tendons are lying at the top and 5 tendons are lying at the bottom. Since the tendons are divided into 2 groups, one above the CGC and the other group lying below the CGC, we are calculating the stress in the concrete at the 2 levels separately. The first procedure will be based on the approximate solution based on the cross section. We are calculating the area of a single wear, which is pi by 4 times the diameter square. Then the total area of the prestressing steel is given as 9 times this area of a single wear. The area of the cross section A is 300 times 250. The moment of inertia of the cross section is equal to the breadth times the depth cube divided by 12. Now, once we know these geometric properties, we can calculate the location of the centroid of the steel. This expression comes from the concept of the first moment of area. That means we are calculating the location of the CGS by calculating the location of each of the tendons, and once we get the location of the CGS, we can calculate the eccentricity, which is the distance between the CGS and the CGC. Here, for the rectangular cross section, the CGC is at the center. What we can see that the CGS is located 150 millimeters from the bottom. Since there are 4 tendons at the top and 5 tendons at the bottom, the CGS is shifted a little bit down from the CGC. The prestressing force is 80% of the ultimate strength times the area of the prestressing tendons, and this is the 435 kilonewton is the total prestressing force applied. The eccentricity of the prestressing force is calculated from the location of the CGC, which is half of the total height, minus the location of the CGS, and the value of the eccentricity is 9.5 millimeters. Now, under this prestressing force, the stress diagrams are: there is a uniform compression if we consider the prestressing force acting at the CGC, plus there is a varying force because of the eccentricity of the CGS from the CGC. Now, the constant value is given as Pi by A, and the varying stress is given as the moment due to the eccentricity of the CGS, which is Pi times E, the moment times the distance from the CGC divided by the moment of inertia. Now, once we add these two terms, we get the final stress profile due to Pi over the depth of the cross section. We can see that the compression at the bottom is higher than the compression at the top because the CGS is lower than the CGC. Our next task in hand is to calculate the stresses in the concrete at the two levels of the steel. We are calculating the stresses based on the stress profile that we have seen before. For the top wears, the distance is given by the half the depth of the section minus the effective cover, and once we substitute that in the expression of the stress, we get the stress at the level of the top steel. That means we are calculating the stress which is the uniform term, it's the first one, and the second one is the varying term which comes due to the eccentricity of the prestressing force. The stress at the level of the top wears is minus 4.9 Newton per millimeter square. We are using a negative value for a compressive stress. Similarly, the stress at a level of a bottom wears is given by substituting the distance of the bottom wears from the CGC. Here the distance is same, which is half the depth minus the effective cover, and when we substitute this expression value of y in the expression of the stress, we get the stress at the level of the bottom steel, which is minus 6.7 Newton per millimeter square, and we see that the stress at the level of the bottom steel is higher than the stress at the level of the top steel. Now, once we have calculated the stresses in concrete at the level of the steel, we are calculating the losses in the tendons at each level. The loss of prestress in the top wears is equal to the modular ratio times the stress in the concrete times the area of the prestressing steel, and that means we are multiplying the drop in the prestress times the area of the prestressing steel to get the total loss in the prestressing force, and substituting the value of the stress at the level of the steel, we get the drop in the prestressing force at the level of the top steel. Similarly, we can calculate the loss of prestress in the bottom wears, which is the same modular ratio times the stress times the total area of the prestressing steel at the bottom, and this is the value for the loss of prestress at the bottom wears. The total loss of prestress is summation of these two terms, and the total loss is 12.3 kilonewton. That means our original prestressing force was 435 kilonewton. From that, we have lost 12.3 kilonewtons due to the elastic shortening. The percentage loss due to elastic shortening is given as 12.3 divided by 435 times 100, and that is 2.83%. That means we have lost 2.83% of the prestressing force due to elastic shortening. The same solution can be done by the more accurate method using the transformed section. Now, the transformed area of the top steel is given as the modular ratio minus 1 times the area of the prestressing steel. Similarly, we can calculate the transformed area of the bottom steel, and then the total area of the transformed section is equal to the area of the gross section plus the equivalent areas corresponding to the two levels of prestressing steel. Note that the transformed area is larger than the original area of 75,000 millimeter square. We can calculate the centroid of the section. This time it is not at the center exactly, because since we are considering a transformed section and the steel is not symmetric about the horizontal axis, the centroid of the section, the CGC itself, is shifted from the previous location, and we can see it is 124.8 millimeter from the bottom of the beam, which is slightly away from 125 which we had seen earlier. The moment of inertia of the transformed section can be found out by using the principles of the parallel axis theorem, that we are calculating first the moment of inertia of the gross section, and then we are adding to that the terms which are the products of the area times the shift in the centroids from the CGC of the transformed section. Now, once we use this parallel axis theorem, we get the moment of inertia of the transformed section. Note that this is also slightly different from the earlier moment of inertia that we had used for the gross section. The eccentricity of the prestressing force is the difference between the CGC, the new CGC, and the CGS. The CGS calculation that we have done earlier remains same for this method of solution also, and the difference gives the eccentricity, which is 9.3 millimeter. Now, once we have got these accurate values, we are calculating the stress at the bottom. It is the same expression, but with more accurate values of the area and the moment of inertia and the eccentricity. With those accurate values, we find that the stress at the bottom is minus 6.52 Newton per millimeter square. The stress at the top is minus 4.81 Newton per millimeter square. Both these values are slightly different from the values that we had seen earlier, and from the stresses in the concrete, we can calculate the loss of prestress in the top wear, which is the modular ratio times the stress in the concrete times the total area of the prestressing steel. And similarly, we are calculating the loss of prestress in the bottom wears, and when we add these two, we get the total loss 12 kilonewton. The percentage loss is 12 divided by 435 times 100 is 2.75%. Now, it can be observed that the accurate and the approximate solutions are very close. Hence, the simpler calculations which are based on the area of the cross section and the moment of inertia of the cross section is acceptable. The additional accuracy that we get by using the area of the transformed section and the moment of inertia of the transformed section may not be warranted, because it leads to more computation. The solution that we get based on the cross section is sufficiently good. We are quickly reviewing the calculation of the loss for the other types of members. For a pretensioned bending member, this is also subjected to camber, and we have to also consider its self weight, because when it comes under a static equilibrium, it is not resting on the prestressing bed throughout its length, but it is resting only at the two ends. Hence, it is subjected to bending along with axial compression. That means, for a bending member, we need to have an additional term in the stress which considers the effect of bending. Due to the effect of self weight, the stress in concrete varies along the length. To have a conservative estimate of the loss, the maximum stress at the level of CGS at the midspan is considered. See, for a bending member, since the stress in the concrete at the level of CGS will vary along the length of the member, it is difficult to have an accurate calculation of the elastic shortening. To simplify the elastic shortening, we consider an overestimate by using the stress at the midspan as the representative stress of the concrete at the level of the CGS. The expression of the stress in the concrete at the midspan at the level of the CGS is given by this expression. The first term is the constant stress. The second term is the varying stress due to the eccentricity of the prestressing force, and since we are calculating the stress at the level of the CGS, the distance is same as the eccentricity. And then there is a third term which is due to the self weight of the member. Since now the member is hogging up, the self weight is acting, and that also creates a stress, and the distance of the CGS is given by the eccentricity. Now, MSW is the moment at midspan due to the self weight. The precise results using AT and IT of the transformed section in place of A and I of the cross section is not computationally warranted. In the above expression, the eccentricity of the CGS was assumed to be constant throughout the length of the member. Next, we are moving on to the post-tensioned axial members. To recollect, for more than one tendon, if the tendons are stretched sequentially, there is loss in a tendon during subsequent stretching of the other tendons. The loss in each tendon can be calculated in progressive sequence, else an approximation can be used to calculate the losses. The elastic shortening is of a concern in a post-tension member if there are more than one tendons and the tendons are stretched sequentially. Since the loss in each tendon due to the stretching of the subsequent tendons vary, the calculation is more involved than a pretension member, and it needs a sequential calculation for each tendon separately. We can approximate this calculation by considering an average elastic shortening for all the tendons. To give you the more rigorous expression, the loss in the first tendon is evaluated precisely, and then half of that value is used as an average loss for all the tendons. That means we are calculating the stress in the level of the first tendon and multiplying that by the modular ratio. This is the loss in the first tendon. In our approximate calculation, what we are assuming is that the average loss in the prestress of all the tendons is half of the loss of the first tendon which has been stretched. And this expression can be written in terms of the initial prestressing force that is applied in the jack, and then we are summing this up by for all the tendons that are being stretched. To summarize, delta Fp is equal to half times the modular ratio times the summation of the prestressing force in each tendon divided by the area of the cross section, and this summation is done from 2 to the total number of tendons. It is from 2 because, as we said, that there will not be any elastic shortening loss for the final tendon, because when the last tendon is stretched, the prestressing force that is recorded by the jack is the force which will not further drop due to the prestressing an elastic shortening. Hence, the summation is from 2 to n. That means, we are neglecting one tendon from the group of tendons which are stretched sequentially. For a post-tension bending member, the procedure is similar. Now, the calculation of loss for tendons stretched sequentially is similar to the axial members. For curved profiles, the eccentricity of the CGS and hence the stress in concrete at the level of the CGS varies along the length. Now, this is another complication, that for a post-tension member, usually the eccentricity varies along the length of the member. Most of the time, the profile of the tendons is parabolic. That means the eccentricity at the midspan is different from the rest of the length. Now, to consider an averaged elastic shortening over the full length of the member, an average stress in the concrete can be considered. Now, this expression is specifically for a parabolic tendon. For a parabolic tendon, the average stress is given by this equation, where this assumes an parabolic variation of the stress. The average stress is given as the stress at the end of the member, which is the lower term, plus 2/3 of the difference of the stress at the midspan and at the end. Again, to understand this expression, that if the stress varies in a parabolic fashion from FCI at the end to FC2 at the midspan, the average stress in the concrete can be considered to be FCI plus 2/3 times the difference of FC2 minus FCI. This expression can be derived from the equation of the parabolic variation of the stress in the level of the CGS. Now, what we have studied today is, first we studied the notations that we are using in our equations. There were two sets of notations. One was the geometric properties. There we learned the notations of A, the area of the cross section, AC, the area of the concrete, AP, the area of the pre-stressing steel, and AT, the area of the transformed section. We learned I, the moment of inertia of the cross section, IT, the moment of inertia of the transformed section, and the eccentricity, which is the distance between the CGS and the CGC. E is considered to be positive when the CGS is below the CGC. The CGC is the centroid of the gross cross section, and CGS is the centroid of the tendons. We have to be aware that either of CGC or CGS may lie outside the concrete section itself, and we have shown that as for an hollow box girder section. Next, we learned the notations for the force variables. Pi is the initial force which is recorded by the gauges in the jack. P0 is the force which drops from Pi due to elastic shortening for a pretension member, and PE is the effective pre-stress which comes after several years after the long-term losses of the pre-stressing force. Next, we moved into the losses of pre-stress. We have seen that the losses can be grouped into two divisions: the immediate losses, under which we have elastic shortening, friction, and anchorage slip. The second group is the time dependent losses, which comes due to creep, shrinkage, and relaxation. And in today's lecture, we covered the first immediate loss, which is the elastic shortening. We saw that this is of a concern for pretension members. We saw the example of a pretension axial members in details. The calculations of a problem showed that if we use the properties of a gross section, the values are close enough compared to the value which is derived by considering a transformed section. Hence, in our subsequent calculations, we shall use the gross section instead of the transformed section. And then we saw the expression of loss for a pretension bending member, where the eccentricity of the prestressing force and the stress created due to the self-weight of the member should also be included. For a post-tension member, we have seen that if there is a single tendon, then we did not have to consider any loss due to elastic shortening, because the force in the jack is recorded after the elastic shortening has occurred. But if there are more than one tendon, and if the tendons are stretched sequentially, then there will be losses in the tendons which are stretched earlier, and the calculation of the loss is done sequentially for each tendon. The process can be simplified if we consider an average loss for all the tendons which are stretched sequentially. The average loss is given in terms of the loss in the tendon which is tensioned first, and the average loss is considered to be half that is seen in the first tendon. Now, in calculating the stress of the concrete at the level of the CGS, we do the summation for all the numbers of tendons except the last one. Hence, the summation is from 2 to the total number of tendons, and like that we get an approximate expression of the loss due to elastic shortening in a post-tension members where the tendons are stretched sequentially. In a post-tension member, if the tendons are having a parabolic profile, then the computation becomes a bit more involved. The eccentricity varies along the length of the member, and hence the stress also varies along the length of the member. For a parabolic profile, we have seen a simplified expression of an average value of the stress in the concrete, which is an average between the stress at the end and the stress at the midspan, and from this average value of the stress in the concrete at the level of CGS, we can calculate the loss in prestress in a post-tension bending member. To summarize, elastic shortening needs to be calculated for a pretension member because the pretension force drops from the value applied by the jacks. It needs to be calculated for a post-tension member when there are more than one tendons and the tendons are stretched sequentially. In our next lecture, we shall move on to the other two types of immediate losses, which are the friction and the anchorage slip. Thank you.